Okay, next speaker is Dr. Jongwoo Lee. He received his PhD degree from the University of Michigan Ann Arbor. From 2008 to 2010, he was an analog circuit designer in Bitwave Semiconductor, Massachusetts, USA. And he is currently a vice president at Samsung Electronic System LSI business. And he is leading the IP design team. Well, his research and products include UWB RF transceivers, high-speed data converters, low-power PLLs, high-speed interface circuits, and yeah, so on. Dr. Lee used to be a TPC member of the A-SSCC, and he is currently a TPC member of the A-SSCC. Yeah, please welcome Dr. Lee.
Thank you for the introduction, and good afternoon, everyone. My name is Jongwoo Lee again, and right before my presentation, Dr. Yoon Chang-soo presented a very nice talk about focusing on wireless transmission, and then I will focus on wireline transmission. So I think it's good balanced. So, okay, then this is outline of my talk. And I didn't realize that my talk is limited to 25 minutes, including questions. So, but I prepared a lot of slides. I'll try to speed up. Okay, and 1848, a gold vein was discovered in California, in United States. Then 1 million of people from all over the world gathered to dig for gold. Then the era of American frontier began. It's a wild, wild west. However, the true era of Western expansion began with the laying of the railroad. And the railroad companies made a lot of money. And today, and many companies are investing to mine data. Today's data is the new gold, and from the gold mine of AI. And the railroad equivalent is interconnect technology. In particular, everyone knows ChatGPT, and ChatGPT brought an inflection point in AI technology. However, there is a big problem about the power consumption. As you may know, the ChatGPT 3 consists of parameter model size of 175 billion, and it consumes 355 million watts. And the ChatGPT 4 training consumes about 10 times more, and it may require 3.5 gigawatt power consumption. That means for each it requires 2 to 3 nuclear power plants, because one nuclear power plant generates 1 to 2 gigawatts energy. Then soon that there will be ChatGPT 5, the training power consumption requires much, much more. Then the power consumption is the big problem. Looking at the advancement of AI technology, core performance has grown very quickly, but the memory bandwidth and interconnect bandwidth is relatively slow. This is due to the main computer architecture based on von Neumann structure. There is a memory bottleneck, so there is a bunch of memory array, and it's separate from the core CPU or GPU processors, and there is a main bottleneck. And ultimately, the core technology is growing very, very fast. Currently, it's exascale, but it will be soon reach to the zettoscale. That means each data center may require power plants for each data centers. So in that case, it will be a disaster. Okay, then first, it would be good to understand the architecture of the today's AI interconnect. There are very important concept about the scale-up interconnect and scale-out interconnect. There are two kinds of interconnect type. And there is a scale-up interconnect that connects vertically within the rack. And there is a scale-out interconnect that connects externally from rack to rack or server to server. So the kind of internal interconnect is scale up, and external interconnect is scale out. Scale out connection is based on the optical interconnect right now, but soon the silicon photonics technology will arise. Then the cost of the optical interconnect will be down. Then the scale out technology will be closer to the scale up interconnect. Okay, looking at the Nvidia DGS H100 example, the connection between GPU here, it's scale up. It's based on the well-known NVLink. So it's currently it's up to 200 gigabps per lane. Then there is an optical interconnect for the external connection. It's based on optical interface. It's a scale out. So it connects each rack to rack and server to server and each data center to data center. And actually this is OSF is looks like that. It's a completely mechanical type of the optical interface, and it's octal, a small form factor pluggable. But when the silicon photonics technology grown, then it will be replaced with the pluggable silicon photonics, and it will be inside the chip soon. Okay, the high-speed interconnect technology is the key expanding bandwidth, and where the scale up or scale out. Recently, the interface over 100 gigabps interface are mainly used, and the main structure looks like that. It's composed of ultra high-speed ADC. It's up to a few tenths of or more 100 gigasample per second ADC, and it's also there is a DSP for channel compensations. And so far, channel compensation is based on with FFE or DFE, and things like MLSD, maximum likelihood signal detection, equalizer based on beta-V decoder used in wireless communication technology. It's also used recently. Okay, then another important chip trend today is combining multiple dies in one package. So it's a multi-chip or chiplet. It's a new trend. Okay, first the MCM. It's a multi-chip module. It combines multiple dies that perform the same function, and there's the chiplet. Its definition is it refers to the die that perform different function for each function that are glued together like Lego to create a single chip. However, these days they are all collectively called chiplets. Okay, so for the future system and package architecture, there are two main things it's focused. So it's advanced packaging for chiplet technology, and there is a system level communication for low power and high bandwidth, including optical. So I'll focus on the chiplet technology first, then move to the optical interface. Okay. The future system in package structure has been well organized by AMD. Its cores such as CPU and GPU are heterogeneously mixed, and dies such as domain-specific accelerators and optical interconnect here. It's co-packaged optics. Then also it includes high bandwidth memory. And all together are combined based on advanced 2D and 2.5D and 3D packaging. Among these, I would like to emphasize die-to-die interface here. Then, and I will briefly introduce the high bandwidth memory. It's a very similar concept with die-to-die interface. Then I will introduce the co-packaged optics. And as computing performance improves, the number of transistors increases exponentially. But now, due to physical limitations, the integration of transistors is no longer improved according to Moore's law. So the chips become larger and larger, which causes serious yield problems. Among various semiconductors, the biggest reason by CMOS has driven technology is because of its cost competitiveness. But it is losing these advantages these days. So we have to split the chips for yield, better yield. And chiplet generation is divided according to the packaging technology, including 2D standard package with a general organic substrate, and 2.5D advanced package with higher density connectivity using separate RDL fan-out or silicon interposer. So silicon bridge is the low-cost version of the silicon interposer. Or the next is ultimately it will go for 3D. And various technology have been developed for die-to-die interface, but they have almost been unified into UCI, which is the most power efficient and fastest. And UCI has been standardized to enable interoperability between dies developed by each different companies. And standard package and advanced package standards have been announced. And the core of UCIe technology is high bandwidth, low latency, and power efficiency, and cost effectiveness. And it generally supports streaming, but it also comparable with existing PCI Express or CXL protocols. So it's very flexible standard. So the most difficult thing in UCI development is the die-to-die layer here. It's an adapter layer, latency, and the channel. Most all the developed should be less than 2 nanoseconds, including adapter layer and channel and file layer. It's very challenging because, for example, there is if the logic is operating 2 gigahertz logic, all the modulation and conversion must be completed within 2 cycles per each side. So at the same time, it is very difficult to design with ultra low power. It's about 0.6 picojoule per bit, but industry, the expectation is less than 0.3 picojoule per bit. So it's very challenging. Also, the small lane-to-lane skew is very challenging too. Okay, this is an example of UCI structure. It has 16 or 64 channels, 16 for standard package and 64 for advanced package at 32 gigabits per lane, and has a single-ended energy and source synchronous structure. So this is an example. And also there's a similar example from Nvidia. Recently, Nvidia announced the Blackwell architecture, and they introduced the first Chiplet architecture with a 2 GPU die and 8 HBM, including. And also, it may be the same, the NV8, okay, it's the same one. Okay, also, the Nvidia published their paper about the die-to-die interface in VLSI 2022. I'm not sure it is the same one with Blackwell NVHBI, but they introduced the synchronous bidirectional signaling, and if the concept is very interesting. Okay, then I'll move to the next topic about the high bandwidth memory. The component HBM is a similar concept of DIMM, in which each DRAM chip is implemented as a module, but each die is stacked of all 3D stacked DRAM cores. And there is a standard HBM is based on JEDEC standard, and today there is a custom HBM for the higher bandwidth and lower power and based on some logic die. And the trend is moving the standard HBM 4 PHY to the UCI PHY. Okay, then the next topic is about optical interconnect. Silicon photonics is an interconnect technology that is receiving a lot of attention in the future, and expected to expand beyond pluggable optical currently used in scale-out interconnect. And they can be expanded to scale up and more diverse field. So it's very similar to the wireless modulation. So it's based on photonic die, and the laser source looks like a RF signal. Then the electric signal looks like a baseband signal. So it's a very interesting concept. So silicon photonics is an interconnect technology. We can compare with a copper-based current interconnect and silicon photonics optical interconnect. What makes optical interface superior to copper is that it's almost no attenuation. There is no attenuation depending on the channel, and the multiple wavelengths can be communicated at the same time. And it's the same in a fiber, on fiber. So wavelength division multiplexing technology is the key of the optical interconnect. Here is the basic example of the silicon photonics optical interface. It consists of electrical IC and photonic IC and fiber channel and transmitter side and receiver side altogether. The main component is modulator, and there is a photodetector. And this is example is the state-of-the-art ring type resonance modulator, but it's very sensitive to the thermal increase. So it's very sensitive to the thermal temperature. So the accurate temperature control is very important. On the otherwise, there is a very traditional Mach-Zehnder modulator. It's very easy to understand. However, the size is too big, almost 1 millimeter, so it's not practical these days. Okay, so this is the very simple concept of the optical interconnect based on Mach-Zehnder. So there is an electrical signal, there is a phase change. So it's constructive or destructive. So there is looks like on-off modulation or amplitude modulation. And photodetector, it's a convert the optical signals to the electrical signal. It's a main component of the silicon photonics. And I put some example of the silicon photonics, so you can see, look at these examples. It's just state of the art. Okay, I ran out. I rushed to finish my slides, and then what's next? Then our future technology is up to you. Thank you.